So, we are discussing about the electromagnetic radiation, and a pictorial representation of it I am going to show you now. Okay. So, this is the pictorial representation. Here I have in this slide, here I have the red one, that is you can imagine a wave along this line, along this black line, a wave going like this and then coming down, cutting it again, going up like this, that is one wave. And imagine another wave perpendicular to that, going like this, and then again coming here and going out like this, etc. So, this is sort of how an electromagnetic radiation will move along this direction. So, it has got a direction, it has the electric field is aligned perpendicular to that, and it is aligned magnetic field is also aligned perpendicular to that in the x, y and z direction. The distance between the two peaks is known as wavelength. So, I think most of you are familiar with the waveforms. We will simply say that all the electromagnetic radiations are characterized by the wavelength denoted by lambda or frequency mu. The term wavelength is defined as the distance between successive maxima or minima. Okay. So, like I was showing you here the every wave has got a reaches a peak point and then it reaches 0 and then it reaches another peak point in the opposite direction, that is negative. So, I have one maxima here, one minima here, okay. One minimum, actually maxima and minima are the plural terms. So, one maxima, one minima, and again maxima, again minima, like that the waves will move on. So, that frequency is the number of cycles occurring per second. So, if I start from this end, now look at the red one, I am marking it here. If I start from here, reach 0 and then reach -1 and then again reach 0 here. So, this is known as one frequency. So, the number of frequencies per second, how much it moves is the frequency per second. So, the number of cycles occurring per second is the frequency. So, how do these two are related to each other? A very simple relation, lambda is equal to mu by v, v by mu, and where v is the velocity of the propagation, and all electromagnetic radiation, you should remember that they all travel in the space with or without matter at the same rate, that is same velocity, that is 2.9979 into 10 raised to 10 centimeter per second. For simplicity we call it 3 into 10 raised to 10 centimeters per second. So, that is the velocity of the light, the speed of light that is visible to us, sun's rays, etc. That is also the same velocity, that is 3 into 10 raised to 10 centimeters per second, or 3 into 10 raised to 8 kilometers per second. So, we can measure the distance between the sun and the earth by the time the sun's radiation reaches the earth and dividing it by the time, by the speed. Okay. So, it is possible for us to determine the exact distance of all planets or all astronomical bodies by the time the light from the astronomical body reaches the earth. So, it is a separate science by itself. Okay. So, we also know that lambda is nothing but wavelength is nothing but frequency speed of light divided by frequency. Now, frequency is expressed as number of cycles per second or as wave numbers. Okay. this wave number is important as far as IR is also concerned, and wave number is given by mu bar is equal to 1 over lambda. So, this also is a parameter we are supposed to remember. So, the distribution of spectral intensity in black body radiation was best explained by Max Planck in 1900 by uniting the corpuscular theory, that is assuming that the electromagnetic radiations are also the radiations containing particles. So, that is the corpuscular theory, and just because it moves in the waves as a wave form, it is also called as wave theory. So, it was considered that is the relation between the energy of a quantum of radiation to the frequency, that is given by delta E is equal to h mu or h c by lambda. That means, the energy of the radiation can be determined if I know the wavelength only. H c by lambda, c is the velocity of light, h is Planck's constant, that is also known, c is known, 3 into 10 raised to 10 only lambda. If I know lambda, I can find out what is the corresponding energy of the electromagnetic radiation. That is very simple. So, here in that equation, delta E is the energy of the quantum of radiation, and V mu is the frequency of radiation, h is in ergs per ergs seconds, that is 6 into 6.24, 6 into 6.624 into 10 raised to minus 27 ergs second. So, the interaction of matter with radiation thus involves the exact quantized energy of the substance. Why? Because all the energy of the wavelength electromagnetic radiation is also quantized. So, every elementary system, whether nucleus or an atom or a molecule, thus has a number of quantized energy levels, which we have seen earlier, that in the form of N, L, S and M, and absorption or emission of energy takes place only if the energy of the matter is equivalent to the difference in the energy states. This is another quantum mechanical theory, that changes in the absorption or emission of energy takes place if the energy of the matter is also equivalent to the difference between the energy states. Otherwise, the radiation is transmitted without any change through the matter. So, this is an important concept we should remember. So, the energy of the frequency, the same equation which same expression which I earlier told, that if the energy has to match the energy of the electromagnetic radiation and of the particles, I can write an equation something like this: h mu, that is h c by lambda, that is the energy of the final state minus energy of the initial state. So, this delta E, this is the energy that is to be matched by the electromagnetic radiation as well as the particulates that are interacting with the electromagnetic radiation. This equation is known as Bohr's equation. So, in this equation, EF and EI are the energies of the final and initial states of the substance. So, in case of emission, the energy of the radiation is given by h mu is equal to h c by lambda, that is EI minus EF. Here I am defining two aspects. One is emission, another is absorption. So, emission is E final state minus absorption is E final state minus E energy of the initial state, and emission is the energy difference between the energy of the initial state and energy of the final state, that is the difference, but the quantum may be same. not maybe, quantum is always same. So, the again in emission EI and EF refer to the energy states of the particulates. So, in actual practice what happens? So, whenever a radiation of multiple frequency interacts, okay, so with the matter, multiple frequency, I cannot choose a radiation with only one single wavelength. That is a little difficult, not that it cannot be done, but I think those of you who are familiar with scientific advances and who are familiar with the science know that we do have laser rays etc., with single wavelength. But in general, if I am dealing with an electromagnetic radiation coming from a particular body, black body or any other body, I get a set of waves having different energies and set of having different wavelengths, different frequencies. It is a bundle of energy. So, the part of whenever I am using I am getting bundle of energy, I call it something like multiple frequency radiation. If I am getting only one single wavelength, then it is a single wavelength radiation. So, when I get multiple energy radiations passing through a given space containing empty space, electrons, neutrons and whatever it is, air molecules etc., lot of things can happen. What can happen? The energy may be used up in absorption, part of the energy may be absorbed by the matter, or it may be reflected by hitting on the particulate and then going off in some other direction. And then another possibility is it may enter a glass like material, go through the glass, bend a little bit and come out on the other side. Okay. So, part of it, some of it, if it is a black color glass or something, all of it will be absorbed and it can be emitted, it can be reflected as if it is hitting something, some hard surface and coming here and going off like this. Okay. It is reflection like a mirror, and then refraction, it passes through the matter, but with a change in the direction, and then it can get diffracted, it can get scattered in all directions, so many other possibilities. So, if we have to consider the interaction of electromagnetic radiation, we should consider all these things: absorption, emission, reflection, refraction, diffraction, scattering and all these things. So, the sum total of the energy when it is interacting is given by the next equation on the next slide, that is E is equal to E absorption. Please look at the slide now. E is equal to E absorbed, energy emitted, energy reflected, energy refracted, energy diffracted, energy scattered and so many other forms of energy, the dispersion. So, that but the sum total of the energy should be same, because that is the law of conservation of energy. I think most of you are familiar with the law of conservation of energy, that is energy can be neither created nor destroyed. The total energy available on the surface of the earth or anywhere else in the whole universe is essentially same. So, it can get converted from one form or another, but you cannot create energy. It is a sort of human restriction. Maybe God can do it, but we do not know. All right. But as far as humans are concerned, the law stands very firm. You cannot create energy, nor you can destroy energy. You can only alter it to some extent. So, various types of quantized energy changes occurring in each region of the spectrum and the magnitude of energies involved have been traditionally used for a variety of spectrochemical techniques, and these energy changes are generally classified into different waves, and these energy changes also have different wavelengths and different frequencies. So, what are the different kinds of energies we talk about, or electromagnetic radiation we talk about? Yesterday I had mentioned during my introduction that electromagnetic radiation will have gamma rays, X-rays, ultraviolet and vacuum ultraviolet, ultraviolet, visible rays, infrared, microwaves, near infrared I had mentioned, and then far infrared, microwaves and radio frequency. So, the absorption of radiation occurring at different wavelengths and the associated spectroscopic techniques I have listed in table 1, that is coming in the next slide. So, I am going a little bit ahead and coming back again. Okay. So, this is the electromagnetic radiation, and you can see here I have plotted, this is a Google picture, I have not plotted. Okay. So, the whole electromagnetic radiation contains gamma rays, X-rays, ultraviolet rays, visible rays, and then infrared, microwaves, and then FM radio waves, and then AM radio waves, and then long radio waves. Okay. Here on the top I have listed the frequencies. So, if the gamma rays, highly energetic electromagnetic radiations are in the gamma rays. Okay. Slightly more than that also will be there in the cosmic rays, but I am not showing you that. Okay. So, our experience is most of the gamma rays range from 10 raised, the frequency ranges from 10 raised to 24 to 10 raised to 19 or something like that. And then comes X-rays having 10 raised to 18 frequency. Then ultraviolet rays are around 16, and visible range are around 15, and frequencies for IR are 10 raised to 14, 12, etc. So, the frequency keeps on decreasing as we go through the electromagnetic radiation from left to right. That means, if the frequency is decreasing, wavelength keeps on increasing. I think you are familiar with that relation now. Okay. So, lambda is equal to 1 over frequency. Okay. So, I have put the wavelength also at the bottom of this strip here. So, the wavelength of gamma rays, if it is 10 raised to 24 per second, 24 waves should pass through a given space, and the wavelength should be approximately 10 raised to minus 16. So, it keeps on decreasing again. That means, waves, the wavelength keeps on increasing, and then it reaches somewhere in here it is all angstroms up to 10 raised to minus 8 centimeter is angstroms, and then it comes here when it comes to IR etc., they keep on increasing. They are slightly longer than visible rays, and then still longer than UV rays, and then it keeps on increasing 10 raised to 0, 10 raised to 2 radio waves, and then long radio waves are all 10 raised to 4, 10 raised to 6, 10 raised to 8 centimeters. Okay. So, that is the increasing wavelength. So, as the frequency increases, wavelength also, as the frequency decreases, wavelength increases. That is the inverse relationship we keep on talking. You should also see that the radiation, here I am showing a small portion with blue, red and green that I have expanded below, and when I expand that below, I get colors like this, that is one side it is dark red blue and another side it is somewhat red and violet. So, the visible range as we experience them covers from 400 to approximately 700, maybe 800 a little bit, slightly more this side that side, it depends upon the individual. Okay. So, the wavelength range corresponding to this is I am describing as in nanometers, not in centimeters or 10 raised to minus 6 centimeter, not in 10 raised to angstroms units or something like that. So, this is where the visible range is there as part of the electromagnetic radiation. So, the types of molecular transitions that occur in the when the electromagnetic radiation interact, they are all I have listed here on the side, that is gamma rays. Whenever you take gamma rays and make them bombard on the element or on a metal, new changes in the nuclear structure take place. That is what I have written, gamma rays nuclear. And if you take X-rays and make them impinge on the metals, I get core level electron changes, that is X-rays, soft X-rays, etc. So, the energy of the matter that comes out would be in the form of about 10 raised to minus 10 centimeters. Then comes ultraviolet, and in ultraviolet region it is the valence electron, that is electrons moving around the nucleus. Those electrons get affected and they may get excited to next higher energy level or lower energy level, and I have listed those interactions as valence electron interaction with electromagnetic radiation. So, these are all atomic and molecular transitions happening in s orbital, p orbital, d orbital and f orbitals. So, microwave also, that is the region where molecular rotations take place and electron spin changes. If you take electromagnetic radiation in microwave, impinge them on the metal elements, then what happens? The electrons will change their spin from positive half to negative half. So, as usual it is like that. Still lower energy radio waves, they result in nuclear spin. Nucleus itself may be moving like this. So, that kind of changes also will be taking place in the electromagnetic radiation. So, this is how then electromagnetic radiation we should visualize, and I hope you are you are fairly comfortable now what we are talking about. Now, in this table 3.1, I am taking the visible radiation. Okay. So, if you remember, here it is 400 to 700, that is the visible range, and that visible range I am cutting into different ranges again, and that is less than 380, most of it is ultraviolet range, and 380 to 435 nanometers is what color of the radiation is transmitted. That means, if the radiation in this range, if I pass the violet radiation, it will pass through the matter. It is just like taking a violet glass and what comes out is violet glass, whatever is the light on the other side. Okay. So, that is known as transmitted light. What comes out on the other side is transmitted. What is held in the glass is the complementary hue. Okay. That is how the glass will look like. Okay. So, whenever electromagnetic radiation passes through a matter, there is there are two components. One is part of it is absorbed, part of it is transmitted. What is transmitted is not absorbed, and whatever is not transmitted is all absorbed. So, suppose I take violet color, violet is absorbed, and the remaining 6 colors from the Vibgyor, they all constitute another color which is known as complementary hue. That is how it looks to us. The radiation coming out will look violet, but the actual material will look the combination of all other colors that are retained in the material, that is known as complementary hue. So, now look at the slide now. From 380 to 435 I have violet color and the complementary hue is yellowish green. The material will look like yellowish green. So, 435, that means if a material looks yellowish green to you as an observer, you should say that it transmits violet color. So, if the material is yellow, then what it is transmitting is blue color. If it is orange, it is greenish blue or bluish green, and green, if it is transmitting green color, it will look purple to you, and similarly other colors like yellowish green, violet, yellow, blue, orange, red. So, you can see that most of these, the transmitted color and complementary hues are approximately inversely related. So, yellow is here and yellow is at the top of the complementary hue, and orange is transmitted around between 590 to 625, but it looks like greenish blue. Where is greenish blue? Greenish blue corresponds to 480 to 590. So, like that any visible range, the transmitted color and complementary hues are different. So, the same thing is true in other radiations also, interactions of the matter with radiations, but we may not be able to see them unless they are in the visible range. So, infrared and many other things, they generally predominantly look like infrared, means it will look like red only. Okay. Microwaves you may not be able to see them at all, and near infrared you can see sometimes color or not, and near ultraviolet you will see them light yellow or colorless. Okay. That is all human eye is capable of seeing the colors. Okay. Now, it must be noted here that there are no sharp differences in color or wavelength. For example, in the previous slide now, I was showing you this is 480 to 435 and this is 435 to 480. Now, what about 440? For 380 to 435 it is violet. How would 440 look like? I have no way of telling exactly, because it all depends upon the observer, your eye, your capability of how good your eyes are, how sharp your eyes are, etc. So, the merging of the colors is sort of in general, to a lot of people it may look the same, but actually a lot of people are color blind also, or it looks different to them. Many times it happens. So, the remaining colors merge into one another in a diffused manner like a rainbow. So, the absorption of radiation involves transfer of energy to the medium, and this process is a specific phenomena related to the characteristic molecular structure. All right. So, for a given excitation process, a molecule absorbs a discrete quantity of an absorption line. However, since a group of molecules exist in a number of vibrational and rotational energy states, each differing by a very small amount of energy, a series of absorption lines appear over a small range, and thus it gives rise to an absorption peak or an absorption band. So, you should look at this slide a little more carefully. So, try to understand what is written here. What I am saying is the absorption of radiation involves transfer of energy, and this process is a specific phenomena. That means, if I had to have a specific phenomena, then the absorption line should correspond to only one wavelength. But actually when you see a spectrum, you see that it is a peak like thing. Now, why do I get a peak? The answer is, for a given excitation process, molecule definitely absorbs a discrete quantity of an absorption line, but a group of molecules exist in a slightly differing energy levels. Therefore, even though the exact quantity of energy is absorbed, the molecule with higher energy, it absorbs the same amount of energy, it appears like a slightly higher. The molecule at lower will appear a little lower. So, with the result that we have a figure like a peak, and that is the reason why we see, instead of a single absorption line, I see a peak appear over a small range that gives rise to an absorption band. Okay. Now, here I am showing you the energy level diagram of different shells, different orbitals. Here it is 1s, 2s, 2p, 3s, 3p, 3d, and then this is 4s, 4p, 4d, etc. And the transition I am showing you here by arrow marks, and you can see that these energies are quantized. That means, if I supply energy somewhere here, it does not take place, the transition does not take place. Only when I supply the energy corresponding to 2s minus 1s, then transition delta E3 will take place. And similarly, between 2s and 2p, delta E2 will take place only when it matches. Okay. So, for monoatomic substances, that means atoms with a single elements with single element, that is hydrogen for example, it has got a single element, nitrogen single element. So, such substances normally exist in gaseous state, very low atomic weight, atomic number, etc. They all stay in gaseous state, and they absorb radiation only through an increase in their electronic energy, that is the energy level between 1s, 2s, 3s, etc. Okay, they transition between 2s and 2p, 3s and 3d, like that it does not happen. So, for polyatomic transitions, that is not the case, because they involve molecular orbitals requiring energy in the ultraviolet region, and these are far more complex, involving vibrational and rotational energy levels. So, the total energy may be considered as the sum of the contributions from all states of energy. So, for each electronic energy state of the molecule, there exist several possible vibrational states, and for each of these vibrational states there are numerous rotational energy states. So, this is what I was trying to explain to you. Many molecules may be in different vibrational energy levels and different rotational energy levels. You can imagine them to be like steps in a multi-story building. So, in a multi-story building, if you want to climb the stairs, you will have to go from ground floor to first floor to second floor, third floor, like that, and then there will be landing. And if you stand at the bottom of a ground floor, you kick a ball to the first floor, it may land on the first floor, or it may land 1 or 2 steps before that, or 1 or 2 steps above that also. So, imagine a molecule is absorbing energy corresponding to 1 step below, 1 step exactly same step, and exactly one step above that. So, all these 3 molecules, if I represent, I get a peak, okay, in terms of energy, that is plotting in terms of energy. So, these energy states are represented as vibrational states for each of these in terms of rotational energy states also. Okay. So, electronic transitions in organic molecules are characterized by the promotion of electrons from bonding or non-bonding orbitals to the excited state anti-bonding orbitals. Okay. So, the bonding orbitals are designated as sigma orbital and non-bonding orbitals transitions are designated as sigma star. Now, you should have a figure like this. I will show you in the next class, but try to understand what I am writing here. The electronic transitions are all characterized by the promotion of electrons from ground state to higher energy state. That means, all electrons bonded in a single bond, double bond, etc., they are all bonding electrons. When those electrons are getting excited by interaction with the molecular interaction with the electromagnetic radiation, those electrons go to a state defined as non-bonding orbital. So, or anti-bonding orbitals, either of them. So, the bonding orbitals are designated as sigma orbitals and non-bonding excited orbitals are called as sigma star. Okay. These are all virtual energy levels. These are all virtual energy levels, not exactly defined. You cannot visualize them in actual practice, but we can picturize them pictorially. We can represent that. I will show you in the next class. So, in addition to many in addition from sigma to sigma star transitions, I have many molecules which may contain many electrons that are not directly involved in bonding, and these are mainly located in atomic orbitals of elements like oxygen, sulfur, nitrogen and halogens. For those of you who are familiar with the chemistry, we know that there are 2 lone pair of electrons in oxygen, which are usually present in water, etc. 2 hydrogen, 1 oxygen, but on the oxygen there are 2 lone pair of electrons. Similarly, there are unpaired unshared pair of electrons on elements like sulfur, nitrogen and halogens, and when they are combined with other elements, we have the generalized shapes of n orbitals can be shown in lines, solid line, dashed line, etc. We will study them in detail in our next class. Thank you very much.